Stanford University.
Okay, so welcome to lecture 15 of CS 193G. Today we have John Nichols from NVIDIA. His role at NVIDIA is as Director of GPU Computing Architecture, and he's here to talk to us today about optimizing parallel GPU performance. So please join me in welcoming John.
Okay, thank you. So please ask questions. I'm going to talk about things at a pretty simple, direct, high-level, first principles kind of fashion. But I know a lot about how all these architectures work because we've developed them right here in Santa Clara. So if you have any questions about how things work, just please ask a question and let me know if I need to repeat it, or if you use the microphone, that's better, I guess. So without any further ado, why don't we jump in? So I think that the key to optimizing performance is to really understand the architecture or the platform that you're running your application or your program on. So the first thing that I like to ask people to do is first really understand very clearly how your application maps onto the architecture in question. And in the case of parallel architectures, which is the case with GPUs, we have a really kind of a complicated scenario. So I'm going to walk through a little bit about, how does the CUDA software programming model map onto this heterogeneous hybrid CPU plus GPU architecture, because we have two different kinds of processors here that are cooperating. So it's helpful to understand that heterogeneity quite a bit. And then I think the biggest rule I always see that people forget about is there's just a whole bunch of parallelism in these GPUs, and you really have to use a lot of parallelism. So we'll talk a little bit about how to really expose lots of parallelism and how to think about it. And I think it helps to a little bit understand how the single instruction, multiple thread instructions work on the GPU, how that colors the performance quite a bit. And then the next big item really is memory. And we'll talk about how to get good memory locality, how to coalesce, how to enable the hardware to do a good job of coalescing memory accesses. And then I think it's important, now that Fermi has more interesting cache support for memory accesses, we'll talk a little bit about how to understand the cache behavior. And then, of course, shared memory is a big deal on all these GPUs because it's an on-chip memory that makes a big difference and allows you to access stuff in much lower latency and much higher bandwidth than you can get going out to ordinary DRAM memory. So we'll talk about how to optimize that and talk about a little bit about memory copies. And then for those who are really curious, we can talk a little bit about understanding the underlying PTEX assembly language instructions. So, and then we'll wrap up. But please ask questions all the way throughout because that's the easiest way to communicate, I think. Any questions about what we're going to go at this point? Okay. So if you recall, so the course earlier went over all the programming model for CUDA, but let me just step back a little bit and talk about the three different levels of, or parallelism scope, okay? Of course, we have individual threads, and then we have thread blocks, which are arrays of threads that cooperate. And then we have grids, which are, if you will, sequences or sets of parallel thread blocks. And these three levels also have corresponding memories, okay? And they're not memories in the traditional sequential computing sense, right? They're really the parallel scope or the parallel level of the memory. So an individual thread has its own private local variables, and those typically reside in registers, but when there are not enough registers, there's a memory that we call the per thread local or private memory. And this is implemented in DRAM on the GPUs you're using in your assignments, but in the Fermi architecture that gets supported by a cache hierarchy, which we'll talk about. So the nice thing about this per thread private memory is that the thread owns it. It's not used for any communications, and you don't really have to think about it too much because registers perform effectively with zero latency, and for the most part you can ignore it, which is very nice. If you just declare a variable in a function and just use the variable, you're going to get the access to go in and out of a register. But if you create a program which has way too much complexity and has way too many intermediate temporary variables, then you'll find that the compiler has to spill those registers, because it doesn't have enough, into the local per thread private memory. And then the whole performance equation becomes much different. We can talk about that. On a thread block, or thread array as we sometimes call it, the shared memory is implemented in a local RAM, which is up close to the processor, so we'll talk about how that maps. And then global memory is used for communications amongst threads that are in different thread blocks and different grids. And we typically have a barrier to communicate between threads in a thread block, and then we need another global barrier to communicate between grids. So that's just a quick refresher. Everybody remember all that stuff?
So I had a quick question about this, and maybe this is coming up, but do you have a slide that relates these ideas, abstract ideas of memory, to where it's actually on chip?
Yeah. So if we go look at that 2 slides ahead. So if we, let me just back up 1 slide. So if you go to the next slide here, we're talking about, we have the CPU, GPU architecture, so it's a heterogeneous thing. So when you write a CUDA program, the serial code wants to run on the host CPU, and the parallel kernel code wants to run on the GPU as threads and thread blocks and grids of thread blocks on the GPU. And this gives us scalability because if I have a GPU with varying numbers or different numbers of processor cores, then that allows me to run different numbers of thread blocks at different time. And if we go and then look at where do functions run, so if I invoke a kernel function here with n blocks worth of blocks and n threads worth of threads per block, then the grid of thread blocks executes on the SM streaming processors, and a whole thread block always maps to a given SM, and it runs to completion on that SM. Now an SM can execute more than 1 thread block. It depends upon how many resources the thread block demands. If it uses a lot of registers and a lot of shared memory, then only 1 thread block might fit. And if it uses just a few registers and a few bytes of shared memory, then it might fit several thread blocks on a given SM. So it depends on, there's sort of a trade-off between how many resources your program uses and how many of those threads you can run at the same time in a given SM. And of course, a big GPU has more SMs, and therefore you can run more of these thread blocks in parallel. And a small GPU, like one on a laptop, runs fewer, and therefore you might only be able to run a minimum of 1 thread block. So when you write a program, you have to think about the fact that the program might only be able to run a single thread block at a given time, and it might run all the thread blocks sequentially on a little bitty GPU. But on a great big GPU, it would try to run as many of them as it can in parallel. So if you look at this mapping here, this is just part of the answer to your question, I think. So the host CPU thread runs on the CPU, and that's generally a heavyweight, fairly coarse-grained, beefy thread. And then all the little fine threads in the thread blocks run on the streaming multiprocessors, the so-called SM processors. And if we go to the next slide, this shows a little bit more detail. So a given thread, which accesses its own private registers and its own private local memory, runs on a given green core. You can see the little dotted line arrow pointing to 1 green core there. So that's one, any given instruction runs on 1 core. but the whole thread block runs in a given SM. So all of the threads in a thread block are assigned to the same SM, and because they need to be able to communicate through shared memory, the per block shared memory, and therefore the per block shared memory for the thread block is implemented as the shared memory RAM, random access memory, in the SM. Does that make sense? Okay.
So the register space and the shared memory space are on chip really the same, or do the looks?
No, so the question is the register space and the shared memory space the same? No, so actually different RAM arrays. So for example, a typical SM might have 128 kilobytes of 128 kilobytes of registers and say 64 kilobytes of shared memory, let's say, or 16 kilobytes of shared memory.
But performance-wise, they're the same.
Similar. So we'll talk about performance a little bit. So the performance of shared memory has a little bit longer latency than the performance of a register. So when you access a register, let's say you're saying add register 1 to register 2 and put it in register 3. So when that instruction goes through the instruction pipeline, by the time it actually executes the add operation, it's already fetched register 1 as a source and fetched register 2 as a source, and then it's going to do the operation. So it looks like it's a zero latency operation. Whereas when you say load a piece of data from memory into a register, that actually has a clear-cut latency, and there's only a certain periodicity at which you can do that. So if you talk about the load to use latency, when you say load a variable out of shared memory, and then I want to use the register that I loaded, that latency might be, say, 10 or 20 cycles. Does that help?
Yeah, that actually.
Okay. So if you look at the dotted lines here, you can see that when the thread block is accessing shared memory, it goes directly to the RAM in the SM, right here. Okay. When the thread accesses global memory on current day machines, it goes straight to DRAM, which is outside the GPU chip, which takes several hundred cycles, typically 200 or 300 cycles of time. In Fermi, which is the next generation GPUs, which you can now get, some global accesses are cached in the L2 cache, and sometimes they're cached in the L1 cache, which is inside the SM. So the advantage of using shared memory is that it's on chip, it's local in the SM, it's very close by, and you can get to it with very low latency and also much higher bandwidth than you can get to the DRAM. So if you're going to read data multiple times and reuse it, there's a lot of value to reading a block of data or a tile of data and keeping that block or tile of data in the shared memory and then accessing it multiple times at lower cost. Yes? The question is, can you...
Specific address space is cacheable or non-cacheable?
Okay. So the way Fermi works is you can designate certain instructions to use the cache or certain instructions to not use the cache. And we'll talk about that. I have a slide coming up a little bit later, so let me know if that answers your question when we get there. Question?
I was wondering where constant memory is in all this.
Okay, the question is, where is constant memory? So constant memory lives in device memory. It's in DRAM, and it's cached in a couple of levels, and there's a cache which is at the L2 level, and there's a cache which is not shown in this picture at the same rough latency as the shared memory. So you can imagine that it behaves like, essentially zero cost once you've fetched a constant. So if you have a single read-only value, which you're going to use in many different threads. In other words, if all the threads are reading the same uniform constant, then this is a very good place to put those kinds of things, is to declare them in CUDA as underbar constant variables. If every thread's going to read a different constant, in other words, it's not a uniform address, then you're better off just reading out of shared memory or out of global memory, because the constant cache is designed to read one small 32-bit constant and broadcast it to all the threads that want to read it. Okay, any more questions about this picture?
I guess there's one more about constant memory. So constant memory also does more in the graphic sense than what we see in CUDA, right? You can do fancy versioning of things and allow SMs to see various constants as you change things. Is that correct?
In graphics, that's true, yeah. And graphics, for example, DX10, DX11 graphics, they use indexed or versioned constants so that they don't have to change the program. For example, let's say you have a program which draws some part of a scene in a game, but it has a parameter. Like, let's say a parameter like, what color is it? So you could write the code so that the code always fetches the color as a constant number 35. And then the software on the CPU side can go in and change constant number 35 kind of from outside, you know, in the drawing sequence, and then change on the fly, change the color, say from blue to red at the right point in time. And that changes the version. So all of the threads which were using version 1 of the constant, let's say blue, keep using the blue version, but at the point that the CPU software changes the color to red, then all of the threads that are created after that time will use the red version, even though they're referencing the same constant number 35. And we don't use that in CUDA because it doesn't really quite fit the C programming model. Yes?
How do you accomplish the versioning?
Sorry?
How do you accomplish the versioning?
Versioning. How do we accomplish versioning on the constant cache? So every tag in the cache has a version number. And so every entry in the constant cache has a number that says I'm version 1 or version 2.
So they all live in the same cacheway and it's in the tag?
They could, yeah. There's multiple ways. I forget how many it's a set associative cache, and there's some number of ways, and I don't remember how many ways there are, but the constant version is.
The number of cacheways limit the number of versions? What limits the number of versions?
Yeah, there's a limit on just how many versions you can have. I don't know what it is. It's what limits it. Good question. I'm not entirely sure. I think there's a limit on the number of bits to encode the version number.
So it's like a counter, and you just.
Yep. Yep. Okay, so the biggest thing that people do that means they don't get great performance is they forget that there's just a whole lot of parallelism in these machines, and it's easy to forget because CUDA virtualizes the amount of physical hardware you have, and CUDA basically creates virtual threads and virtual blocks. And if you think about it, a thread in CUDA is really a virtualized scalar processor. And a thread block is really a virtualized multiprocessor. And it's a combination of the hardware doing this and the CUDA software doing this. There's actually quite a bit of hardware support for this. So when you're programming in CUDA, you're really not programming a particular processor. You're really programming an individual thread, and you're writing a program for one thread, and that virtualized thread is actually created and maintained in the streaming multiprocessor hardware, and that's why we call it a multi-threaded architecture, because the hardware actually creates all these little virtual threads, and that makes it simpler to scale the amount of parallelism and create thousands or tens of thousands of threads. So the other reason we do this is that it allows us to implement a hardware scheduler which makes it zero overhead to schedule all these lightweight threads and keep them all happy and running and fed. And when one thread runs out of work to do, or it's waiting for a long latency operation like a fetch from memory, that allows the hardware scheduler to detect, which threads are able to run and just run those that are able to run. Let's see. Any questions on that one? So the fundamental thing is to remember to just use lots of thread blocks. The number I kind of recommend is I would start at absolute minimum of several hundred thread blocks is a good number. And programs that use several thousand thread blocks are buying themselves scalability. In other words, they will be able to use larger and larger GPUs as the amount of parallelism increases in GPUs. If you just make a little program that only uses a little bit of parallelism, then it may not get any faster as GPUs get more parallel. So if you remember, if you think about how many blocks do you need, you have some kind of a problem and you need to decompose the problem into some number of blocks, some number of threads per block. So if you can think about how to, which threads need to cooperate, if they're going to work on a tile of data or a block of data and cooperate on it, then a typical block count might be in the hundreds or thousands of thread blocks just in order to be able to fill up 10 or 20 or 30 SMs on a given GPU. And that number is likely to increase in the future. Also, because an SM can execute up to 8 thread blocks concurrently, that means that if you have little small blocks with just a few threads per block, you're going to want to have even more blocks. So the purpose of a block, the way to think about a block is that you're going to use it for coarse-grained data parallel decompositions where, let's say, you have a big matrix or a big image or a big array or a big volume of data, and you're going to chunk it up into little tiles or blocks or bricks, and you're going to associate a thread block with one of those bricks or tiles or blocks. So that's typically a coarse-grained data parallel decomposition. And you can also use thread blocks to implement task parallelism. You can say, if I'm block number 1, do task number 1. If I'm block number 2, do task number 2. If I'm block number 3, do task number 3. So you can actually do different stuff in different blocks if you want to, because they're all running independently, and they're all in different SMs. Then within a block, of course, you want to use as many threads as you can, and we currently have a limit of 512 threads per block, and that's probably a good number to not exceed. In general, you need somewhere on the order of 384 to 512 threads in an SM to keep the SM busy. So that might be a good typical starting point to think about, might be to try to aim for 2 blocks in an SM and say 256 threads or 512 threads per block, something in that order. And the more the merrier up until you run out of resources. So the big constraint here is, do you get enough registers per thread and enough shared memory per block to be able to make that program work? And for the most part, the compiler just takes care of that for you, but you can, I think some earlier lectures showed how you could figure out how many registers and shared memory bytes are being used. So that gives you an indication. But just in terms of keeping this machine full, if you take, let's say, 512 threads per block and you want to have 100 blocks or 1,000 blocks, that's somewhere between 10,000 threads to, 500,000 threads just to make the machine happy. So we typically use threads for fine-grained data parallelism, so individual computing a single value, and that's okay. It's because the threads are so lightweight and they're zero overhead for scheduling and basically zero overhead to create and destroy threads, it's all right to have a program which creates a thread, computes one value, and exits. That's just okay. You'll get slightly more efficient if you create a thread and compute 2 or 3 or 4 values and then exit. But it won't be a huge difference. It might be, I don't know, what have you seen for your experience?
There's often an advantage to give each thread as much work it can do while still filling up the machine with thread blocks.
Mm-hmm.
So basically do as much scalar work as you can per thread, just as long as you can occupy all the SMs.
Yeah.
And that's sort of from a to keep the working set small. That's sort of I think there's an argument there.
Mm-hmm. Okay. The other factor that's interesting to note here, we'll get into defining what a warp is, but it's probably good to define thread blocks to be a multiple of 32 threads, just because that's the unit of execution. It's 32 threads at a time. So if you just look at some different size GPUs, here's a small GPU with 32 cores in it. It has 4 SMs. And so it doesn't take too many threads to keep that one busy, but you need 3,000 threads to fill it up. So you'd say, oh, that's a whole lot more than a CPU has threads, right? So you have to really think completely differently about how to use factor of 3,000 parallelism. But I wouldn't stop there, because if you look at typical GPUs, they go from 3,000 threads to 12,000 threads to 30,000 threads. And using 30,000 threads is impossible to do except without some kind of data parallel decomposition. So the only kinds of parallelism that I know about that really scales to 30,000 threads or 50,000 threads or 100,000 threads is to do some kind of association between elements of individual pieces of data and individual threads. So threads abide calculates results abide. That's the most common data parallel decomposition that gives you this kind of parallelism. And if you go to Fermi, Fermi doesn't really have more threads, but it has 24,000 threads, but it does have more instruction level parallelism in that a given thread can do 2 instructions every cycle rather than just 1 in the previous generations. So if we look at the details of single instruction, multiple thread execution, I think you guys have seen this all before, but basically threads run in groups of 32 threads called a warp, and so the instruction dispatchers are up at the top, and instructions flow down to some of these cores, and each given instruction for a given thread always executes on one core. And then there's a bunch of other units here for load store and other special functions. So one way to think about it is if you look at the origin of the word warp, the word warp comes from weaving, and it's a set of parallel threads which comes off the loom. That's why we call this set of parallel threads which do the same instruction, we call that set of parallel threads the warp. And so it's 32 parallel threads in these machines. And if you look at the instruction pipeline, and why is that bouncing? The instruction pipeline flows down through the pipelines in all the processor cores, and each warp executes that instruction on behalf of 32 threads in the warp. And there are predicate bits in every thread, just like they're predicate registers, if you will, very much like 32-bit data registers. But these are 1-bit predicate registers, which the compiler turns on and off to say, I'm going to enable this instruction or disable this instruction for a given instruction. And the instruction dispatch unit basically broadcasts this one instruction, like let's say it's an add instruction, broadcasts the instruction to all 32 threads in the warp, and then those which have their predicates enabled actually do the instruction and then write the result back. And those which have the predicate disabled effectively do a no-op. So when you're thinking about how to optimize performance, to the degree that all of the threads in all the warps are doing the same thing, that's a regular computation. That's going to run really fast because it's going to use all 32 ALUs on every cycle, and everything is completely efficient. If you write an if statement that says if something is less than 0, then do this, then that calculation may disable some threads from doing that operation. And that'll be slightly less efficient, but it's still better to just flow through and do it. There is branching control, and the hardware automatically handles all branching automatically. So it's okay to do irregular computations that have lots of if-then-else statements in them. They work fine. But if you can make a redundant regular computation, it might be faster than one which is irregular and branchy. Any questions about?
I've got a question. Is there a limit to that stack, or since there's only 32 lanes to keep track of, is there a finite limit to what you need to support?
Yeah, so there is a finite limit. The stack is implemented in the DRAM, and it's cached. So, but any given amount of branch divergence is limited to only 32 ways per warp. So if you say if I'm thread 0, if I'm thread 1, if I'm thread 2, or if A is less than B and B is less than C and so forth, you can end up diverging 32 ways so that only one thread is active at a time. But very few codes actually do that. We see most codes typically diverge only temporarily and only maybe at most 2 or 3 levels.
Does that mean whenever I diverge, I use DRAM out of my core?
No, it's cached. So there's a stack in the hardware, and there's a top of stack cache. So you don't have to worry about the DRAM. Every now and then, if you go really deep into your if-then-else logic, it may push a few entries into the next level of stack cache. I wouldn't worry about it. Not a major performance issue. The big performance issue with branching is simply that you're only using part of the machinery on each warp, right? If, say, each time you branch, you may only be using half of the warp is active. Or if you have an if-then-else statement, you're going to execute the sum of the then clause and the else clause. So if you have 10 instructions in the then clause and 10 instructions in the else clause, you'll execute 20 instructions. So the big item, I think, for good performance is memory, optimizing the memory performance. And when we're talking about accessing global memory, which is the DRAM at the bottom of the picture, then the key thing is there to localize all these little individual per thread accesses and combine them together or coalesce them together. So and it's done at a warp basis. So the hardware, you can help the hardware with your program. So if you write your program in such a way that the addresses used by the threads in a warp are all pointing to a small region of memory, then you'll get good memory coalescing in the hardware, and you'll get fast performance. So if you look at typical load store instructions, when you write a C program which accesses a global variable, which is a character or a short or an int or a long, or float or a double, those expand into load store instructions which access 1 byte per thread, or 2 bytes per thread, or 4 bytes per thread, or maybe 8 bytes per thread. And if you look at the PTEX instructions, you'll see instructions like load.64 means load 64 bits per thread, which is 8 bytes per thread for a double precision number, let's say. And the hardware looks at all the addresses from the warp and tries to coalesce them and combine them as much as it can so that it accesses the minimum number of cache lines or the minimum number of memory blocks. So for the 32 threads in a warp, it looks at all those 32 addresses and it says, ooh, which cache lines do they go to? And then it sequentially accesses all the different cache lines that those 32 addresses touch. So some programming optimization rules are try to use addresses that are nearby. So when you're running a program and you're trying to compute an address in an array, let's say, using your thread ID number, the thread index number, with say a unit stride is a very good way to do it. You get very good coalescing with unit stride. And a previous lecture talked about structures of arrays. Oops. What happened here? A previous lecture talked about structures of arrays because they give you unit stride, whereas if you use an array of structures access, then you tend to get scattered accesses where only a few accesses hit in a given cache line, and so you end up accessing many more cache lines and you reduce your bandwidth. So structure of arrays is a good thing. So here's an example of unit stride access that coalesces well. This is just simply using a global thread index I and accessing an array sub I. So you can see that here we've computed I as just the block dimension times the block index plus the thread index. And so this is perfect unit stride. It happens to be a float, but it also works for bigger and smaller quantities. And you just, every thread, so thread 0 accesses element 0, thread 1 accesses element 1, thread 2 accesses element 2. And that's easily coalescible by the hardware, and it will do a good job on that. And that works for both loads and stores. So here's a more messy version, but similar. You can see here I've just drawn 16 threads, but it works for all 32 threads in the warp. Here's one cache line of 128 bytes, and there's a second cache line of 128 bytes that starts here in the yellow and goes down. And this coalesces most of the addresses into the first cache line, and then there's 2 addresses which fall into the second cache line, so we get 2 sequential cache line accesses. These are pipelined, so it's not too bad, but still it's taken basically 16 individual little bitty accesses, combined them, and made them into 2 bigger block accesses, and that's what the hardware does. So when you write your program, if you keep your addresses close together in adjacent threads, threads with close by thread ID numbers, then you'll get this hardware to work for you and do a good job for you. However, you can use it to fetch totally arbitrary addresses, in which case it implements a gather or a scatter. Gather for a load or a read, and a scatter for a store or a write. Let's see, and then there are some interesting rules here. So if, let's say everybody reads or loads from the same address, that's a good case because it just takes that everybody's pointing to the same address, and that just broadcasts that one value to all the threads that want the same value, and there's no issue there. If you have a program which stores, where multiple threads store to the same address, then there's going to be a winner. And we don't tell you who the winner is. And in fact, different machines pick different winners. But sometimes that might make sense. It seems like a nonsensical program, but it actually might make sense. Let's say you have a program which is searching for something and you want to stop the first time some thread finds a result. So it would be okay if you had multiple threads that found a result, as long as you didn't care which one found it. Atomic operations, I forget, have you talked about atomic memory ops? Okay. So atomic memory ops also coalesce. So stores coalesce, loads coalesce, atomic operations coalesce. So a useful unit stride coalescing pattern on atomic operations is to use that to do an update on a histogram. For example, let's say you've accumulated a local histogram in your thread block, and now every thread block wants to go update a global histogram. If you have thread 0 update global histogram bin 0, thread 1 update global histogram bin 1, and thread 2 update, basically thread sub I updates global bin sub I, then you get a perfect unit stride, and you can then issue an atomic add instruction, let's say, to update 32 bins per warp in one instruction. So that goes pretty fast. So in general, the coalescing is a really important thing. If you have divergence here, it can be as bad as 32 different thread addresses hitting 32 different cache lines or 32 different memory blocks, in which case it's going to pipeline it, but still accessing 32 different memory blocks takes a lot longer than accessing just 1 or 2. So you'll see quite a big difference if you have bad coalescing happening. And you can tell by, if you're doing reads, you can just set them all to a constant address and see if the program runs faster. If it does, then that's a strong hint. So talking about pipelining, there are two different pipelines. The Tesla GPUs that are in the lab, I think, right? What happened to threads? Okay, there used to be a thread here. Anyway, when the thread reads or writes memory, a load, for example, is fetching DRAM from global memory and placing it in a register, in the register file, whereas a load from shared memory is reading the on-chip RAM, and that's much lower latency. Same goes for stores. On Fermi, there's a cache hierarchy introduced in the middle. So global loads are cached in the L2 cache, which is a little bit closer to the processor, and you can selectively say whether you want loads to be cached in the L1 or not. There's two kinds of loads, basically. So if you know you're going to reuse data, then it makes sense to use a cacheable kind of load, and there's a way in the CUDA compiler to say whether you want loads to be cached or not. If you're just reading data as a streaming data and you only read it once, and there's no point in caching it in the L1 cache because reading it once isn't going to help you. The cache isn't going to help you. If you're going to read stuff many, many times and you know how to organize it, then you're better off loading it and placing it as a tile or block of data in the shared memory, and then reading it many times from the shared memory. You can sometimes get a similar benefit with the L1 cache. The difference is that when you schedule, because all these loads are pipelined, you can have many load requests in flight. You can have typically 64 pipeline load requests in flight from a given SM. And therefore, if you can organize your code so that you batch, let's say, several load requests per thread up front and don't use any of the results. So like if you say value 1 gets load, gets global memory address 1, value 2 gets global location number 2, then finally those two loads get batched together and it just goes load and pipelines all the way down, brings it back, puts it in the register file. And then if you then consume it in the registers with math operations, then you'll get the good effect of batching those loads together and pipelining them. And that helps you cover up the latency to DRAM, which is on the order of, say, 200, 300 clocks.
Can you coherence
Coherence between L1 caches.
Okay. The question is, are the L1 caches coherent? So this is the L1 cache associated with a particular SM, and this is not coherent with another L1 cache over here on a different SM.
So could you explain a little bit what coherence means? I'm not sure everyone.
Okay. So coherence means that if I have a parallel machine with multiple processors and multiple caches, let's go back to slide. Okay, we'll go to this slide. So every SM has its own L1 cache, which is a blue bar in here, and then there's an L2 cache, which is the big central blue region in the middle of the GPU. Okay, so this particular picture, there are 16 SMs. Each SM has its own L1 cache. Therefore, there are 16 L1 caches. These are not coherent, which is to say, for a given address, each of the L1 caches could potentially contain a different value dependent upon when it read it. If these L1 caches were coherent, then anytime anybody changed a location in memory, they would broadcast that change to all of the L1 caches and update all of the L1 caches so that they are all in agreement or coherent on what the contents of that location are. Now in CUDA, because we say that thread blocks execute independently, we don't need coherence. And it's very expensive and very slow to implement hardware coherence. So because CUDA actually, in its programming model, explicitly does not need coherence, because it says when you execute a thread block, this thread block executes completely independently from all the other thread blocks that are running at the same time. So if I read a piece of data, I must promise, it's a software convention, I must promise that no other thread block is going to change the data that I'm reading. If I do, then I probably have chaos. And the reason I have chaos, if we go back to the original picture of thread blocks, in a given grid, I don't know which of these thread blocks are executing at a given time. On a little GPU, they could execute sequentially, one thread block at a time. On a medium GPU, they could execute, let's say, 10 thread blocks at a time. On a big GPU, they could execute 100 thread blocks at a time in parallel. So therefore, we don't know which thread blocks are running together at the same time. And therefore, if one of them were to change a value in memory, and another thread block were to try to read that same value, we would not know the time ordering or the time relationship between the write and the read. So we just simply say, don't do that. And therefore, there's no need for coherence between writes from this thread block and reads from a second thread block. And we interpose a global barrier synchronization between grid 0 and grid 1, so that if any writes, so that all writes formed by grid 0 are done and complete before we start any thread blocks in grid 1, which depend on it. So if grid 1 depends on grid 0, or if we say grid 0 is a producer and grid 1 is a consumer, then we must have a barrier, a synchronization barrier between the completion of all the producer blocks and the start of any consumer blocks. And that's the synchronization that enables us to not have coherence.
By that barrier, all the data in the L1 cache is flushed into L2 or DRAM.
Right, so we flush all the L1 caches at one of these global barriers so that we invalidate them. Yeah.
I thought the barrier was per thread block.
Yes, I'm talking about two kinds of barriers here. You're right, there's the sync threads CUDA call is a is a barrier within the threads of a thread block. And there's also a global barrier, it's sort of implicit in most CUDA programs, between two kernel calls. If you just write kernel bracket, bracket, bracket.
In the case of two kernel calls, you just end up with another grid 0. It's just two kernel calls, right?
Yeah. So
it's a semantic issue. You were implying that there was a global barrier within,
there is a global,
within a kernel.
So there's two ways to start up a kernel, right? There's a, if you use the normal CUDA angle bracket syntax to start a kernel, then you're implicitly saying that that's a synchronous kernel launch, and it might depend on a preceding kernel. And so the CUDA runtime puts a global barrier in between those two kernels because they might be dependent. However, there is a way to start an asynchronous kernel or an independent kernel such that it does not have to wait or depend on a prior kernel, in which case it will not flush. So when you have this implicit kernel barrier, interkernel barrier, you get cache flushing in between, which is important so that you get proper consumer-producer behavior. I have not done it myself, so there is a separate API that you can use to do independent asynchronous kernel launches, so you can get two kernels going at the same time. Most people don't do that because
right. No,
yeah.
That's interesting. Very cool.
Okay.
Pretty much everything we've taught you in this class, there's a level below it that you can also get to in C++ or out of C. That's a little more nitty-gritty and gives you a little more options. But it's the same programming idea.
Okay.
Actually, another one. How are the C threads calls implemented?
How are the C threads calls implemented?
I mean, just is that? I don't know. Just.
I'm not sure what you mean. So you're saying, how do I launch a kernel, or?
No, he's asking how to sync threads.
Oh, sync threads. How is sync threads implemented? Okay, so sync threads is implemented with a single instruction called bar.sync, bar standing for barrier. And the barrier synchronization instruction is basically a counting barrier. So there's a set of named barriers, so each thread block has its own named barrier in the hardware. And there are two parts to a barrier instruction. There's arriving, so when a thread or a warp issues a barrier synchronization instruction, it first arrives, which increments an arrival count in the hardware for that particular barrier. And then when that count reaches the terminal count, which is the total number of threads in that thread block, then that releases the barrier. So and there's a little bit associated with each warp, which says, am I waiting at a barrier for the barrier to be completed or not? It's all done in hardware. So, as warps arrive at the barrier, they execute their bar.sync instruction, which is what the sync threads compiler intrinsic generates.
And that's all local to one SM.
Yep, it's all local within SM. So there's specific barrier hardware in each SM that keeps track of all the barriers for all the thread blocks. And so each time a warp executes a barrier synchronization instruction, it basically increments the barrier count, and then it waits in the scheduler. The instruction scheduler will not schedule that warp until the barrier is released. And when the arrival count equals the number of threads in the thread block, that releases all the warps, and they're all now marked ready to run. Now they resume. So very small number of cycles elapse between the last warp to arrive at a barrier and the first warp to resume execution, because it's just one instruction. So this is part of the zero overhead or lightweight thread scheduling. It's very important to have fast barrier synchronization if you're going to have thousands of threads all interacting like this. So when you do, for example, a reduction or a scan, you may do 1 or 2 instructions barrier, 1 or 2 instructions barrier, 1 or 2 instructions barrier. So you want that to be quite fast. So in Fermi, we looked at, I guess we were done there. So in Fermi, we introduced this shared memory sort of off to the side, and we partition the RAM between the shared memory and the cache. So in your program, you can decide, do I want to use a big tile in shared memory, or do I want to try, that makes sense if I have a regular kind of structure. But if I have an unpredictable or irregular kind of memory access pattern, I might be better off trying to use the L1 cache. It's worth a try. The L2 cache also speeds up atomic ops because the read, modify, write, let's say I'm doing atomic add to memory. Atomic add to memory has to read the current memory location, add a value to it, and write it back all atomically. So on a Tesla machine, if you go back one slide, on a Tesla machine, the atomic ALU hardware is up close to the DRAM, but it still takes quite a few cycles to do the read, add it in an ALU, which is down here close to the memory, and then write the result back. On the new Fermi machines, the round trip time is quicker because it reads it from the DRAM, caches it in the L2 cache, and then the ALU for doing the atomic read, modify, write is right here, and so it goes much quicker. Higher bandwidth, lower latency. Then, of course, use shared memory. I think you guys already know about this. But the latency, the way to think about it is latency about an order of magnitude lower than the DRAM or the L2, and the bandwidth is about 4 to maybe 8 times higher than DRAM. So if you can, try to put data blocks and tiles in the shared memory when you're going to reuse it. It's good for communications, but don't forget to put in the sync threads barrier synchronization call, because it doesn't work otherwise. Actually, it's kind of tricky. Sometimes it might work, and you might not realize that it was not coded right. So when in doubt, put in more sync threads. But yeah.
Semi-question, semi-comment here. Wouldn't it have been nice if CUDA gave you an actual block load instruction to expose the memory hierarchy in that way? So rather than having to do sync threads and then an element in a shared memory array is for this thread is equal to some data value which all threads execute, and then another sync threads, and rather just have a single block load instruction and say, I just now want all my threads to load, a full DRAM-sized block into this block of shared memory.
Yeah, so the question is, wouldn't it be nice to have a block load instruction to copy blocks of data from global memory to shared memory? Yeah, I think yes. The interesting thing is that the number of different addressing patterns that people want to use is so mind-boggling that when we start looking at hardware to do that, it gets messy really fast. Because if you just say, I can only copy, say, linear addresses, people say, oh, that's not good enough. I want to do a two-dimensional tile. And then you have two different addressing strides, right? You have a two-dimensional structure in global memory, and then you have a two-dimensional tile in shared memory. And you have to describe all of that. If you look at all the instructions it takes to describe it, you end up with a surprising amount of work. So when you distribute it across all the parallel threads of a thread block, it ends up being, a typical case is moving that data from global memory to shared memory ends up being, let's say, 1 or 2 load instructions per thread, plus a bunch of integer addressing instructions. And yeah, it's annoying. I think, so maybe it's a topic for a good, library function. If you can define a good library function that does exactly what you want, then we could imagine how to implement that in hardware maybe, but I haven't seen anybody define one that's clean enough yet. The shared memory is interesting because it's very parallel. So you have all 32 threads of the warp are going to access the shared memory all in the same cycle. And they can do so because there's a big crossbar switch between the thread lanes in the processor and the SM and the banks of the shared memory. So when you do a load or a store between the threads of an SM and the banks of a shared memory, you can get that transaction to go very quickly through the crossbar, but you can potentially get some bank conflicts, and sometimes people really sweat over trying to eliminate the bank conflicts, but I wouldn't worry about it. It's a secondary effect. To a first order, it really, even if it serializes 32 ways, it's still not too bad compared to accessing DRAM. A 32-way diverging access into shared memory is still quite a bit faster than a single coalesced DRAM access. So it's not a big deal, but there are some cases. A typical one is, let's say I have a two-dimensional tile and I want to transpose it or I want to run down the column. Then that's one case where if you run down the column of a 2D tile, which is exactly a power of 2 width and matches the bank count of, say, 16 banks or 32 banks, then you're hitting the same bank all the way down, and that's clearly a bad case. So in those cases, it's worth it to pad the tile with one extra wasted column, which then skews all the addressing so that when you run down a column, it actually goes across all the banks. Puts the column onto a diagonal, if you will. Does that make sense? Okay, using the fact that we have two different machines here means that we have to copy data today back and forth. So you guys have all had to code up this CUDA mem copy where you copy something from host memory into device memory and then have to copy some answer back. And that's kind of a pain in the neck, right? So however, it is done with a fast hardware engine. There's a hardware block copy engine that uses DMA, direct memory access, to copy data as quick as it can, but it's limited by the bandwidth of the PCI Express bus. Typically, we see bandwidths around 5 to 6 gigabytes per second on the current generation PCI Gen 2. So you don't want to do this too often, because if you contrast that with the DRAM bandwidth that you can get with load store instructions in the GPU, there you can get 150 gigabytes per second. Okay, so you don't want to be stuck behind this 6 gigabyte per second bottleneck on the PCIe bus if you can avoid it. So basically, the rules here are just keep data in one place as much as possible, and because of the bandwidth differential, the best place for lots of access is from the GPU side, of course, would be in GPU device memory. And try not to copy stuff back and forth too often. Just leave it there. If you're going to do two kernels in a row, one kernel creates a result and the next kernel consumes it. And then, of course, with these copies, you can do a certain amount of pipelining. You can imagine doing some CPU work, copying data to the GPU, doing some GPU computation, copying data back to the CPU if you have to, and then you can pipeline that whole process so that different kernels are in different phases at different times. And if you balance everything perfectly, of course, it's not usually the case, but if you balance everything perfectly, you can keep all the copy engines busy and keep the GPU busy, keep the CPU busy. This would be a true heterogeneous coprocessing system where you're doing the right amount of computation on the CPU, using the CPU for what it's good at, and doing the right amount of computation on the GPU, using it for what it's good for, and doing a minimal amount of data back and forth. But you can potentially pipeline this whole mess.
This requires the asynchronous kernel launch?
It requires independent kernels so that GPU kernel 1 does not depend on necessarily on the results of GPU kernel 0.
I guess it doesn't, there's no two kernels executing executing at the same time there, but it looks like there's a copy running while kernel's running.
Yeah.
And some code on the CPU is running, and that's not really what I've been writing code to do so far.
Right. If this is more of a case where, let's say these kernels were independent, then it's easier to think about that way. If they're dependent, then you may not need the CPU part at all, right? It may just be CPU sets up the first kernel, and then you have GPU kernel, GPU kernel, GPU kernel, and so you have only the green diagonal.
I guess I'm just asking, how do I get that copy to start running while the kernel's running? And how do I get the CPU to be doing things also while the kernel's running?
So the driver will try to do that overlap for you, but it helps to have what are called CUDA streams. So if you use what are called CUDA streams, the work in a given stream is independent from the work in another stream. So this line here would be basically kernel 0 this is stream 0. This is one set of independent work, and then kernel 1 is a different stream, stream 1, it's independent. That would be one way to do it. Yeah?
I have a question, not extremely related to what you're talking about, but the topic of CPU-GPU interaction kind of triggered in my head. And this is there work on rad-hardened GPUs for space applications, or CPU-GPU pairs that can interact? I'm interested in space-based applications and eventually getting GPUs there. I'd always talk about, the cache architecture. I was curious, what are I guess, if you know anything about what are sort of the roadblocks involved in that in making these things space qualified, rad-hardened at least.
Yeah, so the question is, is there any work going on making GPUs rad-hard for space applications? Okay. Well, quick answer is no. So designing a rad-hard chip is a difficult, long, expensive process, and it's typically not done for really modern processors. It tends to be a lagging thing. So most of the rad-hard processors are pretty ancient processor architectures because designing a rad-hard processor requires much bigger transistors and completely different analog design than what we use. That said, if you look at, I think some people use just plain redundancy on space-borne processors to get the equivalent effect. So I suppose that's an approach.
Okay, because I think like on the CPU side, it's sort of the approach about Pentium 1 that's getting there. That's sort of state of the art. So I didn't know if now that you guys are Fermi, maybe you can rad-harden the old, sort of whatever was GPU state of the art, 8 years ago, say, or whatever.
That would be fun.
No, yeah.
Okay. Skip over that. Let's see. So one thing here's an example of a program where we had a program and the guy said, this program is really, really slow. And we're trying to figure out what's going on. So the horizontal axis here is time, and each bar is the execution time for one warp. And each of this, there's one thread block, or maybe, I forget, there's 2 thread blocks per SM. So each block of red lines is the execution behavior in a given SM. And you can see that most of the warps finish really quickly. And then every now and then you see some warps that run longer. And then this is one warp which runs very, very long time. And the way this program was set up, it had to finish all of the work from all of the thread blocks before it could go on to the next step. And so it had a huge variation in runtime between different threads. Some threads ran short, some threads ran a long time. So the problem was that this program just, one thread could kill the performance for the whole thing.
How can I draw that picture for my program?
This is run on a simulator at home, so I think the CUDA profiling can show you things kind of like this. I haven't seen what it's able to do yet, but anyway, the point I was trying to make here was that if you have a program which has wildly varying runtimes, it might make sense to try to reorganize the code so that it stops itself partway through and reorganizes computations into buckets of work, so that buckets are all about equal the amount of work. And then you have a few long-running buckets and a few short-running buckets, and you don't have to wait for all of the work. So last topic is ptex instructions. If you want to see what the compiler is generating, you can compile with -ptex and look at machine instructions. Ptex stands for parallel thread execution, which is a virtuous instruction set architecture that we use for all of our CUDA programs. And the instructions are pretty simple. They all have an operation type, an opcode like add under op, some kind of a type like 32 bits, or F32 for floating point, or S32 for signed integer, or U32 for unsigned integer, or F64 for double precision. So, for example, add, a floating point add might be add.f64 destination comma source comma source. So if you can dump out the ptex and look at what the compiler is doing to your program, and look at the instructions. So instructions, typical instructions are add, subtract, multiply, multiply, add, fused, multiply, add, divide, reciprocal, remainder, absolute value, negate, min, max. Set predicate means do some comparison operation. A comparison might be equal or less than or greater than. And then if it's true, it'll set a predicate register, true or false. Convert will convert two different data types. Memory instructions are load, store, atomic op, some operation like add, texture, fetch, a surface load or a surface store, and of course branch, subroutine call, return, exit, and bar.sync for barrier synchronization. And the thing about ptex is these instructions map pretty much one-to-one onto Fermi instructions or Tesla instructions when there are enough registers. So when you write a ptex code, or when the compiler generates a ptex instruction, the source and the destination operands are virtual registers. They're just names. And then the assembler maps those onto physical registers. And so if you have enough physical registers to run this program as is, then you'll get a pretty much one-to-one connection between ptex instructions and hardware. So just wrap up here as the last slide. So I think fundamental things really helps to understand the parallelism in the architecture, understand how your application software maps onto the architecture, and then really the key is just to use lots of parallel threads and parallel blocks, and try to keep those addresses local so you don't scatter your addresses all over the place. And use all that memory bandwidth. There's a lot of memory bandwidth if you can get stuff in and out of DRAM instead of limiting yourself to CPU type bandwidths. If you can keep the data in the GPU memory, that helps. And then I guess the best thing is just try it. Experiment, run it, change addresses, try it again, measure the time, and see what happens. So, any more questions?
For more, please visit us at stanford.edu.